defect-based geometrization of generalized symmetries. Yes.
Yeah, thank you very much again for the invitation to this wonderful program. It's an honor to close it. I've already given a formal talk, and this is the last quiet day before the storm, so I thought I should do something for a small audience, which is quite informal. I'm gonna talk about a set of ideas that I started developing a long time ago, 3-4 years ago, together with Matt Bullimore, and then with Lakshya Bharvaj and Sakura Sheffer-Nameki. We haven't published this yet because we went all in various different directions, but it's quite topical and important, I think. And so it's an opportunity to revisit these ideas and maybe end up publishing them. The topic of the program was defects, and I will start from two premises. The first premise, which is something we have been hearing about for months, is that there is a notion of generalized symmetry. And for me, in this talk, they're mostly going to be invertible. Act on extended defects. And if you wish, the second premise is that, well, how would you connect such a topic to geometry? Well, in supersymmetric gauge theories, we know that the IR physics is usually captured by the geometry of interesting moduli spaces of vacuum. So in SUSY QFT, in IR physics is captured by the geometry or by the vacuum geometry. Okay, and yeah, the kind of motivation behind this talk is, well, can we play these games about generalized symmetries acting on defects and capturing, and defects capturing symmetries in a geometric way. So I'm gonna first of all talk about just to let you know about the schedule. I'm gonna talk about. So I'm gonna first of all focus on 3D n equals 4, and in fact very simple abelian theories. The theories that have 8 supercharges. And my main examples will be super electrodynamics, nothing more complicated than that. I'm gonna talk about singular moduli spaces for people who are not very familiar, a fine modular space of vacuum. I'm going to talk about resolutions. Maybe call them zero-form resolutions for reasons that are going to be become apparent later. Resolutions, one form. Anomalies. And two groups. So this is what is basically on the menu today. I will assume some familiarity with two groups and so on and so forth, but not too much. So Oh, how does it work? So let me start by 0. So if you have a theory like 3D n equals to 4, there are a set of 4 or of 8 supercharges. And in particular, you may call them QA A dot, alpha A dot, where these are space-time indices, space-time spinors. And these deliver 2 sets of half BPS defects, or half BPS local operator. These are those that are preserved by either QA alpha plus or Q alpha plus A dot, roughly speaking. They are annihilated by half of the supercharges. And we results in some very interesting phenomena. So the first, not really sure what the best way of doing this is, despite having been here for 2 months, but or 3. But so we have a notion of product. So the local operators form a ring. So this is because within correlation functions, up to if you want Q exact terms, you have a product of operators. And so these operators meaningfully form rings. This is not true in a standard 3D non-supersymmetric QFT or non-protected operators, but there is a way to compute these things within correlation functions, and these products make sense. And then if you know that your theory flows in the IR to some superconformal theory, that you may have a Z plus conformal grading or R charge grading. So they are not only rings, but they are graded rings. And moreover, whenever you have at your disposal topological twist, you can perform something called topological descent, which is not going to be very important for the remainder of the talk, but it endows these rings with an additional structure, which is a secondary product, which tells you that these rings also have some sort of Poisson structure. So I just want to mention it here, but I'm not going to use this too much. It's just an additional structure that you have on these rings. This one? Yeah. So okay. In a few words, if you are in a topologically twisted theory, you can look at topologically a technique called topological descent. You start from a point, a local operator that is topological, and you have a procedure by acting on supercharges and integrating that delivers a 1 dimension higher topological operator. And in 3D, you can start from 1. You have maybe 2 local operators. You do this twice. You transform this operator here in a sphere. You squash it, and you get another local operator. This is another product. And this, right. And two sets of half BPS local operators. They're killed by half of the supercharges. So you get 2 rings. which you may call them R, A, and B, of local operators. And you can think about these rings as algebraic functions on some space. So mathematically, you would say, I take the spectrum of these rings, and this will give me two spaces that are affine algebraic varieties. But it's simply, if I have a ring, I can look at it as a ring of functions. And because of these properties here that I listed, these are conical symplectic singularities.
So the rings subcommittees are not useful.
They're commutative.
Sorry?
Commutative.
Commutative.
Yeah. The commutativity comes from you are in 3 dimensions. You have local operators that you can, that there is no ordering of how they are multiplied. Okay, so this is a bit abstract. But as an example, so a physicist would think that, well, the expectation values of these operators, they're like, they parameterize these moduli spaces of vacuum. So one way to actually compute these rings very efficiently, as I said, I'm going to stick to U1 theories plus some fields in some representations. Let's say plus 2 hypermultiplets of charge 1. You literally have just 2 scalars of charge 1 under the U1, then completed by whatever supersymmetry is requiring you to complete them by. And these scalars, I'm going to call them xi. There you have 4 scalars, 2 for each hypermultiplet, xi, yi. And the moduli space of vacua is the symplectic reduction. These you can think of fields as coordinates on T star C squared. And I1, 2. And the MB is, in this case, the symplectic reduction of this guy by the action of the diagonal gauge group. And if you want to compute it, you have 2 moment maps. One complex one, which looks like this. And one real one.
So x's and y's are based on the fiber of these concentric moments?
Yes, exactly. You have 2 moment maps that you want to set to 0. But standard in hyperkähler quotients that I'm not going to discuss this too much, you can kind of forget about this and work algebraically. And so you get a ring, R0B, which you can define as setting to 0 this guy and taking invariant under the complexified gauge group. This is the ring. And sorry, where is the eraser?
Is it a finitely generated ring?
Yeah. Oh, one is hanging out up here as well. And this is a very nice conical symplectic singularity, and you will recognize it immediately. Invariants under the gauge group, you can package in a matrix. So the gauge group acts with weight 1 on the x's, with weight -1 on the y's. So they are matrices of this form, but I'm setting to 0 the complex moment map. And you can, these are the gauge invariant guys. And this is simply UVZ such that UV is Z squared. This is the only time in the talk I'm going to go to such details. But these are functions on C2 mod Z2. So this is a nice cone with a singularity here. All right, and I hope this is sufficiently clear. All you need to keep in mind is that we have these two rings, and we have a way to compute one of them at least very efficiently, and it's a symplectic singularity. But how about symmetries? Super QED with two hypermultiplets has a symmetry that I'm going to call GB, which is PSU2. These are the automorphisms of C2 mod the action of the gauge that is diagonal. So it's PSU2. And this GB acts on MB, which is C2 mod Z2, faithfully by rotations. So the symmetry of the theory manifests themselves as the automorphism of this space. Okay. This is pretty standard so far. But now, what people want to do is often, since you want to approximate IR physics by like sigma modems into these spaces. If you have singularities, this is bad. But what you can do is you can try to resolve them physically by introducing some parameters. And usually, what people do is they would introduce what I would call zero-form resolutions. So there is a resolution of singularities, which is this RP1 goes to C2 mod Z2. And often, the standard way to think about this is that in order to find these moduli spaces of vacua, we were setting a complex in the real moment map to 0. And you can kind of resolve this space by setting the value of the real moment map not to 0, but to something slightly bigger. If you look here, we have x1 squared, x2 squared. If we have something slightly positive here, at least one of these two cannot vanish. Right? And this means that you're parameterizing a P1. And the other moment map is telling you that the other coordinates kind of parameterize the cotangent direction. So usually what people do is they take the real moment map and they introduce a parameter here, which is physically it's an NFI parameter, which is a background parameter for a topological symmetry, for a U1A topological symmetry. Topological symmetry is a symmetry that in 3 dimensions acts on monopole operators. Monopole operators are operators in the other ring, are A. So you can resolve one space by using symmetry for the other space. But what is important is that it's just a background parameter for some symmetry of the theory RA, U1A.
Is also the other, like if you take the reality condition.
Yeah.
Do we get another cone or do we get something else?
Sorry, what do you mean?
here we put the complex map to 0,
Yes.
and then we found there is this.
Yeah.
If we put the real map to 0, do we get the same?
So this is with the real moment map to 0. If you modify the real moment map, you get T star P1. It's a resolution of this thing. You basically have you blow this up to a P1, and this is the cotangent direction.
Where did we put the real map to 0?
I just worked algebraically, so you forget about it. It's hidden in this computation. Okay, but so what I want to say is that you can resolve these spaces by using backgrounds for symmetries. But this is not quite satisfactory from a defect point of view. So we can take a more, to this standard way, so we can take a more algebraic or a defect-based resolution of this thing. So more algebraically, or let's say, yeah, for defect-based, or more algebraic defect-based approach, you can do the following. We had the ring of local operator, R0B. We determined what it was. Their functions on C2 mod Z2. But now consider a charge 1 Wilson line. Is a charge 1 Wilson line. And ask yourself what are the local operators that can end on this line. The operators that can end on these lines are R0B, but then multiplied by x1, x2, because they absorb the charge of the Wilson line. They are not gauge invariant by themselves. They have charge 1. The Wilson line absorbs this extra charge. But then how about V2? And I'm realizing I'm going very slow. Okay, this is the same thing, but you can have charged 2 operators that multiply your original ring. So you can ask yourself, what kind of structure has the ring of operators that sit at the bottom of a line?
I get why the first thing's gauge invariant. I don't understand what you're talking about. So I don't understand what the...
It's a charge 2 Wilson line.
Oh, that's okay. Sorry.
Yes.
Now I understand it. Sorry.
Yes. Charge 1, charge 2. So you absorb the charge by yes.
Sorry.
Yes. So I noticed that W2 comes from fusing W1 with itself twice. So what you can consider is pick W1 or W and consider the ring of local operators, the sum over all n's of the ring of all local operators that sit at the bottom of a power of this line, which I'm going to call Rn. And the claim is that so this is a positively graded ring. There is an operation that you can take. Before we took the spectrum of this ring, if you have a graded ring, you can take something like proj of this graded ring. So remember, Rn are the operators sitting at the bottom of the W1 to the n. And if you took this algebraic operation here, proj of Rw, what you get is indeed T star of P1. This is how algebraic geometry think about projective space. But it's, yeah. basically determined by a graded ring of basically the closed sets are zero sets of homogeneous polynomials, where the homogeneity is given by this grading. And the Wilson line itself that we pick, W equals W1, is actually a line bundle on this T star P1, which is the ON, the pullback of the ON line bundle on P1. These are simply the functions of homogeneity degree n. And so another way of saying this is that RVW is the sum over n greater than 0, T star P1 ON, the sections of these line bundles here. So this was perhaps a bit quick if you are not familiar with such constructions, but each line determines a line bundle over the moduli space. This is part of this Proch construction. And these operators here are like the sections of these line bundles, this line bundle. And although you cannot reconstruct projective space from simply functions on it, you can reconstruct it from sections of a line bundle. And physically, the sections of this line bundle are the local operators that sit at the bottom of a Wilson line. Now, how does this relate to what we said before? Before I was introducing an Fi parameter, which was like a background for asymmetry. And the fact is that this Wilson line here, I lost the red, so this Wilson line here has this peculiar property that if you introduce background bundles for the other symmetry and you measure the first Chern class of these U1 bundles around this line, you get 1. This is for the charge 1 Wilson line. So this means that the Wilson line is what we call a solitonic defect. It generates backgrounds for symmetries. And in particular, it generates backgrounds for this topological symmetry. And this is why we call this a zero-form resolution. You are resolving the space by a defect that induces a background for U1A. And it's in a similar fashion as before, we were resolving the space by introducing background connections for this. All right. Are there any questions so far? Yeah, for this symmetry, yes. And the Fi parameter that I introduced before, you can think of as the bottom component of perhaps complexified connection for this. So the effect is the same. We just given an algebraic approach, defect-based approach on such resolution. Right. Okay. Now, sorry? Yeah, so the Wilson line here, you have a discrete spectrum that cannot do much. If you fuse them, you're going to get another one. And if you look at the gauge charge, it's just the sum of the gauge charges. You may have more intricate defect spectrums, of course, but these ones are fairly simple.
You're looking at Fi parameters, mean you're limited to U1 symmetries here? Or?
No, I mean, Yeah, usually the existence of such resolutions arise when you have these U1 factors. So in that sense, yes. But what I'm going to say later, not much. But in order to resolve these spaces, you always need a U1 in some ways. Yes, or at least that's the most standard way. The lines.
Yes.
Yeah, I mean, in this, there is a meaning to what it means to fuse two lines, and not much can happen. In this case, they simply form a group set. All right. So this is just rephrasing something. I think I said two. So let me talk about one-form resolutions. Can use. So let us look at another theory, which is I still take a hypermultiplet, but now a Z2 gauged hypermultiplet. So this means that my hypermultiplets are functions on, I have a U2 or a U2 or a SU2 symmetry acting on the free hyper, and engaging a Z2 subgroup of this. The Z2 subgroup, and if I take invariants under this Z2 subgroup, what I get are functions like this: x squared, y squared, xy. These are all the functions that are invariant under Z2. I'm acting +1 on x and -1 on y. Is that clear? Yeah. One is +1 and the other -1 under Z2. And if you look at this, lo and behold, MB is the same as before, is again C2 mod Z2. I get exactly the same equations as before. This times this is this squared. And in this case, going back to Chris's question, we have no topological symmetry. There is no U1 in the gauge group. So we have something that is, again, a cone, but there is no U1 I can resolve it with. So what can one do? Yeah. Yes. So how can you get a smooth object in some sense? And here I'm going to take a little bit of a leap of faith, but the fact is that if you think about this simply as Z2 mod SC2 mod Z2, you are kind of forgetting that there are unbroken gauge symmetries on top of this space. So at the tip of this cone, where here is the identity, you have an unbroken gauge symmetry, and you can think of having here above this point a space which is a point mod Z2. Some mathematicians would say that this is a very simple instance of the fact that a gauge theory is like a sigma model into a stack. But if you want to forget about these words, here just think of a space that keeps tracks of the unbroken gauge symmetries. You have a point mod Z2, and in fact, like sheaves on this are basically the Wilson lines that live there. All right. So the point is that if you think in terms of defects, I have two Wilson. I have one non-trivial Wilson line because I have a Z2 gauge group, And away from this point, all the Wilson lines are screened. If I give a vev to one of the x's, I'm going to have x1, for instance, that screens my Wilson line, or y1. But so this is away from origin. At the origin, the Wilson line is not screened, and you have these two Wilson lines, the -1 and the +1, that fuse accordingly to Z2. And so, if we remember this fact, we have a moduli space which is C2 mod Z2 everywhere, but at the origin, I have a space that remembers about this these unbroken gauge symmetries. And in fact, this kind of object is what is called a smooth stack. So although you cannot resolve it as a variety, you can still build a smooth object, which is a smooth stack. And we call this a one-form resolution because these Wilson lines that you use to remember the unbroken gauge symmetry, they are charged under a one-form symmetry. So you have the charge 1 Wilson line, and if you take a background over this disk of the one-form symmetry, this is non-zero. All right. So to sum up, you want an enhancement of the previous moduli spaces that knows about which Wilson lines are screened and not screened, and therefore keeps tracks of the unbroken or broken gauge symmetries. And if you put this together, you get something that is smooth in a mathematical sense. Yeah, they're not screened anymore, so they are there, and they have this product. And so you have something on top of that origin, effectively. It's like you have a TQFT, which is like it is like a diagram Witten theory on the tip of the point. But these Wilson lines you can think of. Yeah, they're building part of a TQFT that sits at the tip of the point. And everywhere else, they are just screened and they disappear in the IR. Yeah, exactly. They have no vevs. It's just because of that. Yes. Right. So, okay. Maybe. So, okay, we talked about resolution, and this was kind of a warm-up. Perhaps of interest in this sort of program was one of the many topics of interest were, for instance, how do we capture things like anomalies from extended defects? So let me talk about anomalies. So I'm going to go back to my previous example. A U1 gauge theory plus two hypers of charge 1. And as I told you before, I had two symmetries. One is GB, which are the automorphism of these two hypers that commute with the gauge group. And these are an SO3. And I had a GA, which was this topological symmetry, which is a U1. And as it turns out, there is a mixed Toft anomaly between these two things. So this is something that people have computed in various ways, including myself. In terms of a 4D SPT phase, you could write something like
So what is GA? U1? What?
U1. it is of this form here. W2B is an abstraction class to lift an SO3 bundle to SU2 bundle. And C1 is simply the first rank class of the U1 mod, the U1's topological symmetry mod 2. Okay, so we have this anomaly, and we want to capture it in terms of defects. We want to see it effectively on the defects. And in these papers I listed at the beginning of the talk, we took this perspective that you can actually reconstruct these anomalies by indeed looking at these solitonic defects. So if you remember, I had my...
What is inside the exponential? 2 pi over 2.
2 pi I over 2.
Which is pi I, yeah.
W2B cap C1A mod 2. Yeah. Yeah, exactly. Precisely. And so we had, so remember that we had a Wilson line of charge 1 that we can consider powers thereof. And so here we had W0, W1, W2, and so on and so forth. And here we have these rings that I called RB1, RB0, RB2, and so on and so forth. And in order to resolve the space, I told you that these Wilson lines, they generate background for U1A. They generate backgrounds for the topological symmetry. So if I integrate over a disk this C1A, I'm going to get something non-zero. But then you can notice the following. You can ask the question. This was R0B, X1, X2, and so on and so forth. Sorry, maybe let me write down another one. Okay, do you all remember this picture? Reasonably clear? Yes. And I moreover told you that these Wilson lines here generate backgrounds for the other symmetry, for the U1A. And now you can compare which backgrounds they produce. And here is, if I integrate C1 mod A, I get 0, 1, 2. But whenever the background they create is odd, if you look at the symmetries that act on the local operators at the bottom of these lines, they transform in a projective representation of SO3 or on representations of SU2. These are doublet of SU2, and then you get a SO3 representation, and then SU2 one, and then SO3 one. And so you can kind of correlate the background for one symmetry that they produce with an extension of the other symmetry. This allows you to define a homomorphism from the center of one symmetry to the other. And moreover, looking at this way, you can convince yourself that there is enough data to precisely write down this thing. Like the anomaly is encoded in how the representations, or how one symmetry is centrally extended when acting at the bottom of some local operators. It's something that has to do with symmetry fractionalization and so on and so forth. And so this is what I was doing with Matt, Sakura, and Laksha in some of the papers I wrote down. But now, this is very powerful, by the way. You can compute loads of anomalies this way. And you can compute symmetry enhancements and all sort of things. It's quite remarkable. But the topic of my talk was not exactly this, but was geometry. What does it mean geometrically? Like, what does this anomaly mean at the level of the moduli space? This is the question. So you may remember that I told you that the Wn Wilson line is a line bundle on my resolved moduli space. Do you remember this? And the rings of local operators sitting at the bottom of these lines, they represent sections of this line bundle. And the translation of the anomaly in geometric terms is that, so geometrically, Wn is SO3 equivariant. Only if n is even. Okay. So this is the statement of the anomaly. You can rephrase it geometrically this way. You use a line to resolve the moduli space. It ends up being a line bundle on that space. And the anomaly that we saw is the fact that this line is only SO3 equivariant when n is even. When n is odd, it has sections like these ones that transform in SU2 representations. So the anomaly represents an abstraction to make these line bundles equivariant.
Seems like a very fancy way of saying we either have a number of
It's the important thing is which representations they transform on. It provides a map between some information about one symmetry and the other one. And in this U1 case, it boils down to a computation that is what you said. But more generally, you can consider more general theories with more general groups, and you just need to. It's all part of how does the symmetry faithfully acting on local operators act on other extended defects? Part of that sort of thing. And if you think about geometrically what is happening, it's more or less what this is what I said here. Right. So you could play a similar game with the Z2 gauge hyper. But in the last few minutes, let me mention the two-group stuff. So let's see. So when people in high energy theory were looking at two groups, some of the first examples were coming from gauge theories with a center that does not act faithfully. So let me transform my example, my simple example, into something that has a two group. I'm gonna consider a U1 gauge theory plus two charge, two hypers. Now the hypers have charge 2. And so there is a Z2 subgroup of U1 that acts trivially on the hypermultiplets. All right? And if we enhance the picture I had before for the Z2 gauged hyper, I need to remember that I had this Z2 unbroken gauge symmetry at a point. Here I'm going to have a Z2 unbroken gauge symmetry everywhere. And so I have something like this. This is C2 mod Z2. But above each point of this C2 mod Z2, I have an unbroken Z2 gauge symmetry. I can think of as having some TFT that represents this thing. And I can remember this sort of things if I define an object MB, which is, instead of taking a symplectic quotient of T star C2, I take a stack quotient of this thing here. This is what some mathematicians defined as stacky proj. But physicsy or pictorially, you have to imagine that I have an honest moduli space, which is C2 mod Z2, and above each point, I'm remembering the unbroken gauge symmetry. And now, what is we have so this theory here has a one-form symmetry gamma, which is Z2. It comes from the part of the center of the gauge group that acts trivially. And this sits into a 2 group with the SO3. So this is gamma A, zero form symmetry. Sorry, gamma B, zero form symmetry. GB is SO3. And these two things sit into a 2 group, meaning that the one form symmetry and the zero form symmetry interact in a non-trivial way, which you can see in several ways, and which is dictated by a Poznikov class, which is in H3 of BSO3 Z2. All right. No. Trivial action, non-trivial Poznikov class. And you can, physicists were studying this by looking at certain short exact sequences. I have not gonna really have time to write down, but it's pretty established material. But geometrically, what is happening here is that you have gamma A acting on the fibers of this, and you have, sorry, gamma B acting on the fibers of this, and you have GB acting on the base. GB are the isometries of the C2 mod Z2, as I told you before. The Z2 one-form symmetry are the Gukov-Witten defects generated by Gukov-Witten defects that act on the Wilson lines. Z2 Wilson lines I have on top of this. So you have a nice geometric action on this object here. And in fact, mathematicians have computed automorphism to groups of this sort of stacks. And the claim we have is that we have two claims, I think, at least I have two claims, is that the two group symmetry of the theory so this two group here is isomorphic to the automorphism to group of this object. Automorphism to group of MB. So I have a space that I build this way, and it is acted upon by some zero form symmetries and one form symmetries, and these coincide with the symmetries that are present in the theory in the UV. And you can kind of to show something like this, you need to match up how physicists compute things and how mathematicians compute automorphisms to groups of these spaces. And it does not seem too difficult. But then there is the claim 2 that I can justify further if you like. But remember that I was capturing the anomaly between the zero form and the zero form as an abstraction to equivariance of some line bundles on the space. And the claim is that theta is, and similarly, an abstraction to the equivariance of this space here, this BZ2 fibration over here. A BZ2 fibration over C2 mod Z2. I can explain how this works. but let me just throw it out there. So like the Poznikov class captures the abstractions to this thing here, which in this case is called a gerb to be equivariant. I have a bit Z2 fibration, and the way in which this bit Z2 fibers does not interact very well with the SO3 acting on the base. Yeah. Yeah, I mean, it's essentially the same picture. Yeah, but it's a little bit geometrized. You know, yeah, I can explain later. But yeah, it's very similar to. I mean, the anomalies I talked about before in the two groups are very closely related. One is like one level up version of the other. And you see these things you can see very clearly. If anybody's interested, I can explain later. But I think I've reached the 1100 point, so I might close it here. It's fine. I think I think I'm just going to conclude that. So in this program here, all we want to do is to try to use these enhanced geometries of the spaces to characterize these generalized symmetries, their anomalies, two groups. These things interplay very well with the 3D mirror symmetry. You have, we managed to map global forms and anomalies of groups and anomalies across 3D mirror symmetry, and then you might ask yourself how these sort of geometric pictures interplay with these sort of things. And then you may ask, well, how about non-invertible symmetries? And in the case of non-invertible symmetries, we would enter a territory that is perhaps less geometric in a standard sense that it is, but can also be studied, and it's just future work. Yeah, no, but I think this is a good place to stop, and so I thank you for your attention.
More questions?
So you said anomaly of two groups.
Sorry?
So you said anomaly of two groups? Is it?
No, sorry. I may have misspoken. We are not really studying anomalies of two groups. We are studying anomalies in the zero form sense, and two group structures between 0 and 1 form. And these two things are closely related to each other. You can go from the model I introduced before and this other model by gauging the topological symmetry by Z2. And so there is a way to translate issues about zero form anomalies to issues about two groups, but no anomaly of two groups. I mean, you can try to study those two, but I mean, yeah.
Kind of like big picture questions, like if you could improve whatever result you want tomorrow, or there could be several results, then what is the ultimate hope to like?
Right. So yeah, correct. So I think for me the ultimate hope is like I think what people are realizing slowly in supersymmetric gauge theories as well is like historically you want to characterize theories with rich moduli spaces of vacua as like sigma models into these spaces. But if you work purely at the level of the space as a variety, you might miss some things. And what you miss is when you flow to one of these points on the moduli space, there might be some TFTs that arise on top. in 3 dimensions, the TFTs can be very interesting because they can be braided modular tensor categories or things like this. But also in 4D, I think people got close to a classification of 4D TQFTs. I kind of lost track, but in any case, what you want to see is how does the physics look like at low energy around a point. And you don't only want to keep track of that piece of information, you want to keep track of what happens when you move around points to that TQFT. And this way of packaging things, like this abstraction to equivariant equivariant gerbs and so on and so forth, are first steps towards a global understanding of how effective TFTs behave on top of moduli spaces of vacua. And well, the motivation is just to study this sort of framework that is quite classical better, but and also to connect to people that have been doing mathematics. So you can try to match with constructions that people have done in maths and try to make this kind of folklore that, you know, a gauge theory is like a sigma model into a stack, so a little more precise, and imports the generalized symmetry setup. But for me, personally, you know, behind all of this, there is like really a defect-based understanding of these symmetries. Like there are these defects that generalize, that carry the actions of these symmetries, and there are these defects that you want to extract spaces from. And so it's an angle that you can take to ask how much do defects know about the symmetries. How much, or you can reverse the question, how much of the symmetries we know actually matter from the point of view of the defects? How much information they carry. So in general, they will form representations of these generalized symmetries. And you want to ask how much information these representations carry. Can I reconstruct the symmetry from the defects and so on and so forth? And this is a geometric playground where you can try to answer these questions. You build geometric spaces, compute automorphism groups, and is there more than that? It's also in a UV-IR flow, if you like, because most of the defect symmetries most of the symmetries you compute from defects, they are like UV-like. We have these Wilson lines and so on and so forth. When we talk about moduli spaces, it's like going a little bit in the IR. And so you want to know how the symmetries computed in the UV and the IR match up. The zero-form symmetries made nonce and so on and so forth. But yeah, so it's to wrap up the answer to my question is a way of encoding these effective TQFTs at points around moduli spaces and the global structure of that, which has been a little underappreciated, I think, over the years, and which interplays very well with this generalized symmetry community.
Other questions? I feel like I should have a follow-up also. Not sure when.
We'll see each other again.
All right, let's thank Andrea.